Alright, welcome back to Meteorology 101. In this video, I'm going to do a quick video on atmospheric structure. So visit my website, meteorology101.com, and I have an article on there with the different atmospheres for the different planets. So a lot of information. So visit my website, like, share, subscribe to my channel. So atmospheric composition, we talk about what's in the atmosphere, mostly oxygen and nitrogen. So 78% nitrogen, 21% oxygen, and then the other 1% is inert gases such as argon. There actually are about 14 other gases that make up that 1%. So methane, helium, hydrogen, nitrous oxide, the ozone, ammonia. So that 1% is basically a whole lot of other gases that really don't have any major impacts. So the layers of the atmosphere, we're going to get into a little bit of detail on each one of these. There is the exosphere. We don't cover on this chart. That's way out into right there on the edge of space. So that's what allows some molecules escape out into space in the exosphere. So these are the ones we're worried about. Most of our weather, really what we're concerned about as a meteorologist, are the troposphere and the stratosphere. Anything above that, really not a lot going on up there. You can see on this chart in the troposphere how the temperature decreases with height. The tropopause is the transition between the troposphere and the stratosphere, and then you have an increase of temperature with height on the stratosphere, and that's a stable layer. And then the transition to the mesosphere, and then another decrease in temperature with height, and then the mesopause, which is the transition between up to the thermosphere. And then the thermosphere absorbs most of the heat from the sun. That's what protects us. And you see a very sharp increase in temperature with height in the thermosphere. And also the ionosphere is located within the thermosphere, and that's what's important for radar signals, is they're electrically charged ions that can transmit radio waves through that part of the atmosphere pretty efficiently. So the word troposphere means the changing sphere. So that's the layer of the atmosphere that we live in, and it's constantly changing. So that's why it was named the troposphere. It extends from the surface to approximately 10 kilometers, which is about 32,000 feet, just under 33,000 feet. So a pretty thick layer of the atmosphere where most of the weather happens. And it does vary with height, with season and latitude. So you have lower heights at the poles and higher heights at the equator. So as the equator heats up, you have those higher heights. Now your height does change. You have more of an oval atmosphere around the Earth if you think about it with heights. The troposphere contains 80% of the atmosphere's mass, with all the water vapor, clouds, precipitation in the atmosphere. So to create a cloud, there has to be CCN. It's a condensation nuclei for the water vapor to condensate to. So that is even more of a mass in that lower part of the atmosphere. Strong vertical mixing occurs in the troposphere, which may be caused by mechanical turbulence, mixing due to the frictional effects of the surface of the Earth, and air molecules travel through the depth of the troposphere in a few days, and in thunderstorms, just over a few minutes. So, with the wind blows with the pressure gradient force, high pressure blown into low pressure, and makes contact with the surface of the Earth, that creates a friction, and then starts a rotation and small eddies that will cause the mixing that will mix that atmosphere, and then you'll have actually with the troposphere you'll have a decrease in temperature with height, but with the mixing, when that mixing occurs and gets into a little bit higher levels, then you'll have a slower decrease in temperature with height, so it'd be more consistent because of that mixing. You're mixing warm air with the cold air. So there are four main layers of the atmosphere that concern meteorologists: the troposphere, stratosphere. We spoke about those two. And within the troposphere, there's the planetary boundary layer and the free atmosphere. So the planetary boundary layer is a portion of the atmosphere affected by friction of the Earth's surface. So that's pretty much around the Earth's surface. Anything that affects friction, causes friction with the wind, is the planetary boundary layer. So that's going to be buildings, trees, mountains. So now your planetary boundary varies with height depending on the roughness of that surface. So the planetary boundary layer is a portion of the atmosphere affected by the friction of the Earth's surface. It extends from the surface to the gradient level, where friction is zero. So that it will extend up to the gradient level, where friction is zero. Once that hits that gradient level, then that's where the gradient level begins. There's no friction, and that is considered the free atmosphere. So the molecular boundary layer extends from the surface to about 1 centimeter. That's pretty much on the surface. Pretty much mixing is completely suppressed, and conduction is the primary method of heat transfer. So as the air hits the surface of the Earth is hotter, then it will heat the air, and that is your conduction. And the surface layer extends approximately 10 meters, which is about 33 feet. So it doesn't go up very high. The surface layer that contains a microscale mixing. The mixed layer extends to about 1 kilometer, which is about 3,200 feet, and contains greater mixing, but is still affected by friction. So we'll get to the next chart here, and if you can see the very bottom of this chart with conduction, that's your molecular boundary layer. Pretty much all mixing is suppressed, and then the conduction heats that part of the air, and then that air will rise and then create those small eddies up into the surface layer, 1 meter to 10 meters. And then you'll get into the mixed layer, which is between 10 meters and 1 kilometer. Then those eddies will increase in size, and then the eddies get large enough to mix the heat upward more efficiently, because you're getting into those areas where there's a lot lower friction. And then once that air particle is raised to the height, as our temperature decreases with height, once that air particle is cooled to the dew point, that's when you have 100% saturation and clouds form at that level. So that is the free atmosphere. Now, there is a level of free convection. Don't confuse that, because in thunderstorms, as convection starts, you can reach a level of free convection where that thunderstorm can take off and rapidly intensify. This free atmosphere is where basically there's no friction. Friction is zero. The heating occurs, and this is just this more or less is going to be your condensation level. So your convective condensation level, just based on a hot surface, causes an air particle to rise, and then once it reaches that level where it's cooled to the dew point, that is your convective condensation level, and that's where the cloud is going to form. So you can find that level on the SCOOT chart. It's a CCL, and then you'll have the LCL, which is a lifted condensation level. Now, that's the level at which a particle has to be raised to form clouds based on lift. If a frontal system comes through and forces that air particle to that level, if it's forced up, where's the cloud going to form? That's going to be the LCL. If it's rose up by the heat, just the heating of the Earth, then that cloud is going to form at the layer of the convective condensation level. So two different cloud levels that you can get from the SCOOT. So the planetary boundary layer. The boundary layer is part of the atmosphere where the Earth's surface affects air motion. So we talked about that. Friction. The top of the boundary layer is called the gradient level. That's usually about 2,300 feet. And it's lower over the oceans, which because you have less friction over the water, and higher over the mountains because you have a higher level of friction. So that top of that boundary layer is around 2,300 feet. Well, if you're in the mountains, obviously if the mountain goes over 2,300 feet, that boundary layer, is much higher. The top of the boundary layer is much higher. The gradient level is where there's no friction. So once you hit that level where there's no friction affecting that airflow, then you've reached the gradient level. All right, so the troposphere is the lowest layer of the atmosphere, contains nearly all the Earth's weather. That's the part of the atmosphere we live in. Temperature normally decreases with height, and height varies with mean temperature and ranges from 7 kilometers near the poles to 17 kilometers near the equator. Now, if you look this up, you can get different readings. Typically, you can go to 17 to 20, 8 to 10 kilometers, near the poles. So that will vary based on temperature, based on those heights. Higher pressure, colder air has lower heights. So like we said, the atmosphere is thinner at the poles than it is at the equator. And as you get in the summertime, you're going to have higher heights at the equator than you are at the poles also. Alright, the Tropopause is just a transition between the troposphere and the stratosphere. It's marked with a sharp decrease in the amount of water vapor and a rapid increase in the amount of ozone. The Tropopause ranges from 10 to 20 kilometers above the Earth, which is 32,000 to 65,000 feet. So the top of our atmosphere that we live in is right around 32,000 feet. Now, that doesn't mean there's not weather above that layer. In the Tropopause, the weather can push through the Tropopause very easily. Once it hits the Stratopause or Stratosphere, that's where you hit a very strong stable layer, and that will suppress weather significantly. So the word stratosphere is a layered sphere. Stratosphere extends 20 kilometers to 47 kilometers and extremely stable. So we just talked about it will suppress most weather that hits that layer. The lapse rate through the stratosphere shows an inversion, which is an increase in temperature with height, and very little mixing occurs between the stratosphere and the troposphere. Strong thunderstorms can penetrate only a few kilometers into the stratosphere, the overshooting tops, which is pretty impressive because it is such a strong, stable layer. When the thunderstorm goes up, it can actually still shoot through that stable layer and cause the overshooting tops that you'll see on satellite and radar. When you look at the echo tops, if you do a cross section on radar, you can see that. So with mixing being suppressed, because of the stability. So very, very stable layer. Increase in temperature with height. Warm over cold is a stable layer. Cold over warm. Cold air wants to sink. Warm air wants to rise. So that's an unstable layer. So that's the layer of the atmosphere we live in. A very unstable layer. So particles can remain in the stratosphere on the order of years. Debris from past nuclear explosions and dust from volcanic eruptions are present in much higher concentrations than in the troposphere. So because it is a stable layer, that will just sit there. Another thing to think about too is with the stratosphere, when we say these temperatures increase with height, they do increase with height, but you're still talking, you're 20 kilometers up, about 65,000 feet. So there's really nothing warm about that. So the temperatures can increase from about a negative 60 degrees Fahrenheit to about 5 degrees Fahrenheit. So that's your increase in temperature with height. So negative 60 to 5 degrees. So you're still you're still freezing up there. All right, Stratopoles, just a transition between the stratosphere and the mesosphere, and that's about 47 kilometers to 55 kilometers throughout that transition, and that's still pretty high. It's about 150,000 to 180,000 feet, which is about 29 to 34 miles. The Mesosphere is middle sphere. That's the definition for mesosphere, and extends 55 kilometers, 78 kilometers. So now you're looking at 34 to 48 miles up for the thickness of that layer. The top of the mesosphere is about 0.01 millibars. We send balloons up to go through the atmosphere to get data. They don't even make it near this far. So accounts for 0.099%, approximately 0.1% of the atmosphere's mass. So there's really nothing there. Temperature decreases with height, so it has a positive lapse rate, just like our atmosphere. And the vertical motions are not suppressed. So anything that does make it up through that layer will continue to rise, or you can get convection in that. Not really convection, but you can get instability in that layer, because it is an unstable layer, just like the troposphere. So there's a name for some clouds that do form in those upper layers. You can actually look at pictures on the internet for those. The mother of pearl is a nickname for it. Let me see if I can find that real quick. And that's a nacreous cloud, is I guess the official term for that cloud. Alright, the Mesopoles is a transition between the mesosphere and the thermosphere. So it's about 78 kilometers to 98 kilometers. Then now you're talking 48 to 60 miles high. Okay, the thermosphere, this layer extends from 98 to 500 kilometers, so that's all the way out to 310 miles out. Temperatures increase with height. It has a negative lapse rate, very stable. And the reason that temperature increases with height, that layer of the atmosphere absorbs most of the heat from the sun to protect us on Earth. Temperatures range from 5,000 to 2,000 degrees Kelvin and are directly proportional to the amount of solar activity. The heat source is the absorption of solar radiation by molecular oxygen, and the ionosphere is an electrified region within the thermosphere where there is fairly large concentration of ions. This region is important for radio communications, so we spoke about that earlier. In the exosphere, we didn't have it on our chart, but this is the outermost layer of the atmosphere. It extends from the top of the thermosphere to about 6,200 miles above the Earth. So that's a pretty thick layer. And in this layer, atoms and molecules escape into space, and satellites orbit the Earth. At the bottom of the exosphere is the Tropopause, located around 375 miles above the Earth. So 600 kilometers. Alright, you can see that we have a decrease in temperature with height, a transition between the two layers of the atmosphere up into the stratosphere, and then a significant increase with height, and then another transition, a decrease with height in the mesosphere, and then a transition up to the thermosphere. And like so we said, there's the exosphere is the outer part of that, which we don't even really concern ourselves with. The main thing we concern ourselves with is the troposphere, a little bit of the stratosphere that you can get through the Tropopause, overshooting tops, and you can reach up to about 60,000 feet, or just over 60,000 feet with a thunderstorm overshooting tops. That's just going to, and a pretty good indication of how strong that thunderstorm is, how strong that updraft is in that thunderstorm. And then that boundary layer, the molecular boundary layer, which is the friction on the surface, conduction, heating of the air, and then creating those eddies and creating clouds at the convective condensation level. And then the level free atmosphere, where there is zero friction, the gradient level. So right above that is where you're going to get, and that's way down here in the troposphere. So once you hit that level where there's no friction, then that's where you're going to see the winds are going to be mostly parallel with the contours in that layer. So if you pull up a SCOOT chart and you hit that layer of free atmosphere, there's nothing affecting those winds. They will stay pretty much parallel. And we'll get into the next video I'll do. We'll get into those charts, and we'll start pulling some upper air charts and show you different layers of the atmosphere as seen on a weather chart. So this is just to give you a overview of each layer of the atmosphere and how these they affect weather. So thanks for watching. Subscribe to the channel, and until next time, get your head in the clouds.